Hello, and welcome back, biologists, to round two of our examples of how to solve these Punnett score problems. So this is going to be another single trait problem with just a little twist from the last time. But before we begin, I'd like to pull up this whole thingamabobber here that says number one, we're going to define our alleles. Number two, we're going to determine the parent genotypes. Number three, gametes, four, Punnett square, and five, the answer to the question and the ratios. This is something that we're going to start every single problem with, so I'm going to keep bringing it up to get you familiar with it. If you keep these steps in mind and even outline them on your paper, it'll help you show your work in the right way and make sure you get all the information organized, because that is the hard part about these questions. It's just organizing all the information it's giving you and making it work for you in a Punnett square. So let's go to the next page, as this is going to like twinkle again. Remember, alleles are versions of a gene. We have our dominant and recessive alleles for any given gene. The dominant will mask the recessive. Genotype is a pair of alleles. So you get one allele from each parent, and then the offspring will get the genotype with like the two alleles, just the pair of alleles together. And that can be homozygous, heterozygous, homozygous dominant or recessive, and we'll speak more about that in a second. Gametes, those are the possible alleles a parent can pass on to its offspring. So if they were homozygous and they had two of the same allele, they'd only have one possible gamete. But if they were heterozygous and had two different alleles, they could pass on two different gametes. That ties into the whole easy way, hard way thing that we're going to see again here. Then we're going to make a Punnett square, obviously, because we're doing Punnett squares. And then with that Punnett square, we can use that to find our genotypic and phenotypic ratios of our children. And I will remind you too, the first thing we always do in these problems is read them super, super carefully, because all the information is always buried inside these sentences, and it's up to us to organize it and unpack it and let it do work. So, without further ado, dimples is a dominant trait. A woman without dimples and a man with dimples carrying the non-dimple allele have a child. What are the genotypic and phenotypic ratios of their children? So I'm going to invite you to pause for a second here and define the alleles. Remember, you can pick any letter you want here. D works pretty well because D for dimples, but like you want to make sure the big thing is that the letters look different, not positive, uppercase and lowercase, because if they don't, you're going to get confused, and I'm going to get confused, and everyone's going to get confused. So take a second. Okay, so for dimples, I went with the letter D, nice and simple, but you'll see what I mean here is the capital D looks very different than the lowercase d. If we were doing something like a P or an S or the letter C or something like that, you could see how that would be confusing. You want something that's clearly differentiable. So here we've defined our alleles. We have dimples as dominant because it says dimples is a dominant trait. So we're giving it the capital D because the capital letter is always for the dominant allele. Then no dimples is recessive, so we're giving it the lowercase d. Perfect. Now we have to determine the parent genotypes. Remember, a genotype is the pair of alleles that the parent has. So again, I'll invite you to pause it for a second here, work ahead and try to figure out the genotype of each parent. So I'll give you a second. All right, so if we read this very slowly, it goes, a woman without dimples. So that straight off the bat tells us that the woman is going to be homozygous recessive, no dimples, because they have the recessive phenotype. So they have to have two recessive genes. If they had any dominant genes here, they'd be having dimples. They'd have dimples. So because they don't have dimples, we know that they're homozygous recessive. Then it says the man has dimples, but is carrying the non-dimple allele. That means he has dimples, so he must have one dominant allele, as we see here. But he's carrying the non-dimple allele. That means he has it in his phenotype, but it's masked by the dominant one. So even though it doesn't show, it's still present. If you think back to the pea plants, this is why we saw a white flower in the last generation, but not the second one. Interesting. Anyways, with that in mind, determine the possible gametes that each parent can make. Again, I'll give you a second here. All right, so for the male, they're heterozygotes, that's the word for something that's heterozygous. They can make either gamete because they have both type of alleles. You see, he has both a big D, a dominant allele, and a little d, a recessive allele, so he could pass on either to his children. Whereas the female only has little d alleles, so she can only pass on the little d recessive allele. See how that works? The male has both, so he could pass on both. The female only has the one type of allele, so she can only pass on the one. With that, let's try to make our Punnett square. Again, with this one, you'll notice that the mother can only pass on one type of allele. So there's a way to shorten this Punnett square that we'll see in a second. Okay, so here's our nice little Punnett square. We're going to line it up. Female always goes on top. Remember, the female's always on top of the Punnett square, always, all the time, because she just is. So here, we have two recessive alleles, because the female can only pass on recessive. You might see where this is going. But we can get rid of that whole column because these are the same. Let's just see what happened there. So these are both little d. So no matter what you're mixing them with, they're going to do the same thing. So we can just cover up one and only do the cross once. And at the same time, we're adding on the male's gametes here. So the male is heterozygous with a dominant allele and a recessive allele. So there we have to do both because you see if we cross a big D, it'll be different than if we cross a little d. But with the female, they're both little d's, both recessive, so we can just do the one side. This is going to save you time and frustration and keep a cleaner paper. So I recommend doing that if you notice that happening. So anyways, we can make this cross happen now. We can just take this big D, the dominant allele, and the recessive allele, cross them here, and then two recessive ones here. So we end up with two possible genotypes here. We have the heterozygous offspring and a homozygous recessive offspring. So with that in mind, pause the video for a second and try to make a genotypic and phenotypic ratio. All right, so here a genotypic ratio is 1/2 heterozygous. That means 1/2 dominant and recessive alleles in one, and then 1/2 homozygous recessive. So there's two possibilities. They each take up one of them, so they're each 1 out of 2. Fraction-wise, that's for phenotypes. The one that has the dominant allele will be the heterozygote, so there'll be 50% dimples, and then the homozygous recessive one is 50% no dimples, because half of them have dimples and half of them don't. So, good work, biologists. I'm going to keep putting examples up, so keep checking back. And once again, feel free to email me, mrbsciencemb@gmail.com, if you have any requests or further questions. So yeah, have a lovely day.